For the William Tell problem, we did some algebra to come up with this equation, sometimes called the William Tell equation, that relates the launch angle and the launch speed to the range of a projectile that lands at the same height from which it is launched. But there's more to learn about the path of a projectile like this. After all, it's a pretty common scenario where something lands at the same height it's launched from. Think tossing a football. So let's look in more detail about that sort of projectile. Okay, so I've got events 1, 2, and 3. This time I'm calling event 2 when the projectile is at its highest point, and 3 when it lands over here. And let's compare its launch velocity to its landing velocity. Going to our equations here, I can take a look at this last one. If I'm comparing events 1 to 3, then I guess this changes to v3y right here. So from launch to land, the change in the vertical position, the change in y, well, here's its initial y, there's its final y, they're the same, so final minus initial is 0. Delta y is 0. So if the left-hand side is 0, that tells you the right-hand side is 0. Well, you know it didn't take 0 time to travel that distance. Therefore, this quantity here has to be 0 as well. v1y plus v3y equals 0. That is, the sum of the y components of the initial and final velocities is 0. So from this equation here, delta y is 1/2 v1y plus v3y delta t. That's 0, therefore this is 0. Therefore v1y has to be the opposite of v3y. The y components are equal and opposite. You may have predicted that from looking at the situation using your intuition, saying, oh, this here has to be equal and opposite to this here. And we just proved it using this relationship. So that's a key conclusion about a projectile like this. The y component when it launches is equal and opposite to the y component when it lands. But now you may also point out that, oh, the x components of the velocities, we know that those are both the same. That hasn't changed the whole time. Therefore, if this side is equal to this side, and this side is equal to this side, then the speeds must be equal also. The hypotenuses here must be the same. These triangles must be congruent. Therefore, we also have the launch speed has to be equal to the landing speed, v3. Second important conclusion there. Furthermore, if the two triangles are congruent and the sides are all equal, then this angle here has to be equal to the corresponding angle on this triangle, which would be this one right here. And by opposite interior angles being equal, geometry tells us that this angle, since this angle equals that angle, it also equals this angle. Therefore, theta 1 and theta 3 are equal as well. So the angle at which it launches is then equal to the angle at which it lands. So we've got this perfect symmetry between the two endpoints if we're launching and landing at the same height. Okay, how about the midpoint here? To figure out some information about the midpoint, let's first look at the total travel time along this path. Back to our equations. Now that we know about the initial and final y components of the velocities, we can use this equation here, since we know that, to get the change in time. So next equation, we'll say that delta Vy is opposite g delta t. So if we look at moments 1 and 3, v3y component minus v1 y component is negative g delta t. We showed a moment ago that these two are equal and opposite, or v3y is the opposite of v1y, so I could replace it with opposite v1y minus v1y. Therefore, the left-hand side is negative 2 v1y. I can divide both sides by negative g and end up with delta t equals 2 v1y over g. So that is our travel time. So delta t here we could write as t3, that's the final, minus t1, which we could set to 0. So t3, the time when we land, is given by this expression here. It just depends on the y component of the initial velocity. Okay, I'm going to come back to this in a moment, because now I want to find how long does it take to get to the very top. Well, you might say from your intuition that it's going to take exactly half the time to get to the top as it does to get down. Or maybe you think it's going to get down more quickly than it takes to rise up. We can settle that question right now. Let's use the same equation and look at the travel time from events 1 to 2. So, same equation, delta Vy is negative g delta t. This time we'll go from events 1 to 2, so Vy2 minus, V2y minus V1y equals negative g, and then this delta t will be t2 minus t1, but again t1 is 0. We start the clock there. Okay, what about our y component at time 2? Well, if that's our highest point, our velocity is tangent to the path at that point, it must be perfectly horizontal at that moment, therefore it has no y component. V2y is 0. So I'm left with just negative v1y equals negative g t2, or t2 equals v1y over g. Compare these two expressions, and you'll see that t2 is exactly 1/2 of t3. There's t2, and this is 2 times t2 right there. Conclusion is that the travel time up equals 1/2 of the total travel time. Another way of putting that is that the time up is exactly equal to the time down. We just proved that the time it takes to get to the highest point will be exactly equal to the time it takes to get back down once again. Okay, another key conclusion about projectile launching and landing from the same speed. I've got one more to figure out here. Let's look at the distances horizontally that are traveled here. Going to this equation right here to look at the horizontal distance traveled. It just depends on how long you've been traveling. So, x3 here, well, let's write down our equation. Delta x is Vx delta t. So let's compare traveling from event 1 to event 3 to event 1 to event 2. So x3 minus x1, so this is events 1 to 3, equals Vx t3 minus t1. Well, x1 is 0, t1 is 0. And then comparing events 2 to 1, we could say x2 minus x1 equals Vx times t2 minus t1. Again, x1 is 0, t1 is 0. So that tells us that x3 is Vx times t3, and x2 is Vx times t2. I'm going to divide these two equations by each other to cancel out Vx, which is common to both of them. Vx is the same in both of them here. So x2 divided by x3, that equals Vx t2, this divided by this, divided by Vx t3. The Vx's cancel out, so I've got the ratio of these two distances equals the ratio of these two times. Well, we showed a moment ago that t2 is 1/2 of t3. So this equals 1/2 of t3 all over t3. So t3 cancels, and we find that the ratio of these two distances is 1/2, or x2 is 1/2 of x3. x2 is 1/2 x3. So what we just showed there is that this distance here is exactly half the total distance traveled. Something you probably could have predicted. Our parabola here is perfectly symmetric. The time it takes to get to the top is equal to the time it takes to get to the bottom, and the distance it travels to the top is exactly equal to the distance it travels from here to there. There we go.